Hey, it's Matthew, and in this video I'm going to be deriving the lever rule and showing how it applies to dew and bubble temperature graphs. So, for starters, we can say that the total number of moles in a system is equal to the total number of liquid moles in the system plus the total number of vapor moles in the system. And this is assuming there's no solids in the system, of course. Say we have a component I and it makes up a specific percentage, say Z percentage of a system. Well, we can say that the percentage of component I times the total number of moles in the system is equal to the molar ratio of liquid of component I times the total number of liquid moles in the system plus the vapor molar ratio of component I times the total number of vapor moles in the system. Well, from here we can sub in L plus V for F and then distribute, and we get percentage of I times the total number of liquid plus the percentage of I times the total number of vapor, and that is equal to its liquid molar ratio times the total liquid plus the vapor molar ratio times the total vapor in the system. And from here, if we want to get L all on one side, the total liquid moles on one side, and the total vapor moles all on one side, we can rearrange this equation so we have the percentage of I times total liquid moles minus the liquid molar ratio of I times the total number of vapor or liquid moles, and is equal to, that should be a minus, and is equal to the vapor molar ratio times total vapor moles minus the percentage of I in the system times vapor moles. So YIV minus ZIV. Now from here we can draw out L and V. So the total number of liquid moles is equal to the percentage of I times the percentage of I minus the liquid molar ratio of I, and that is equal to the total number of vapor moles times the vapor molar ratio of I minus the percentage of I in the system. And from here, we can get a ratio of the liquid to vapor moles in the system, and it is equal to this term over this term. So the vapor molar ratio of I minus percentage of I divided by percentage of I minus the liquid molar ratio. And so what if we have our dew and bubble temperature graph? So our temperature and our molar ratios of component I, and our liquid curve and our vapor curve. So the vapor curve, liquid curve. Now, as you remember from previous videos, as we raise the temperature of a specific molar ratio, we eventually have all liquid, and we begin to form gas. We begin to form a vapor of that component. And that temperature that we reach when we begin to form the vapor is the bubble temperature. And as we lower the temperature and we begin to form liquid from the vapor, we then find our dew temperature. And so say we know the temperature, say it's right about here. Hopefully that's straight. And so we know the temperature. Well, from here we can find the vapor curve here, so the vapor molar ratio of component I, and we know the liquid molar ratio of component I. Well, so now that we know the temperature, we can find two of the variables in our lever equation right here. And say we know the percentage of component I in the system, or component 1 in the system. Well, now we know all of the variables on this side, so we actually can just solve for a percentage or a ratio of the total liquid moles in the system to the total vapor moles in the system. Now, another important thing to mention is the reason why this is called the lever rule is, say we have this line here, and we know these two molar ratios. Well, this and this can be looked at as a distance from, say, this is going to be zi. yi minus zi, or in this case, this will be z1. y1 minus z1 is this distance, and z1 minus x1 is this distance right there. And so, say we call this distance A, and that's distance B. Well, now we know that the total, or the ratio of total liquid moles to the total vapor moles in the system is just equal to distance A divided by the distance B.